Hi, in this video, we're going to talk about the active high and active low. Remember that all the information is well written and organized in the lab manual, and everything I will mention, it's been in the lab manual. Previously, we mentioned the differences between the LED pins and the longer side and the shorter side. Keep in mind the longer side they represent the positive and the shorter side represent the negative or the cathode. And in this video, we're gonna see that this way is called the active low, and the way is called active low because we need a low signal in order to activate it. As you can see here, the longer pin is connected to the positive through the resistor, which in turn is gonna limit the current. Keep in mind that low signal should be on the cathode because it's an active low. Let's talk now about active high and active low. What does that mean? First, we're going to talk about the active high. As we can see here on the left side in this picture, also on your lab manual, here we have at the point, this point in the green, we're going to have the input, which is the signal that's going to come. When it's 1, the LED going to be on. Now the resistor, we have it to limit the current. Now keep in mind that this box here represent the LED. So the positive represent the longer side and the negative represent the shorter side. The shorter side is connected to the negative. On the other side, we have the active low and what is currently just were plugged into the breadboard. The 5 volt coming from the power supply, and then it's go through a resistor, and then this part represent the LEDs, the red and the green and the yellow. And the input signal, when it's come 0, it's turned the LED on. That's represent the active low. And this is what it simulate what was in the breadboard. So each LED have 2 pins, number 1 and number 2. The longer one is the positive. If the longer one was going to the 5 volt on the power supply, as you can see here in the circuit, then this is represent active low. Here, if we have the power supply, this is just a simulation how you plug the active high. From the negative, you go to the cathode of the LED, and the positive always go to a resistor, and then the signal gonna come from this point, and that's gonna represent the active high. Here we gonna use the active low, and this one, the active high, we don't gonna use it, so that's why I indicated in the X mark. When we have a high volt here, the LED gonna go on, but here when the LED gonna go on when we have a low signal or 0. Next, we're gonna talk about DeMORGAN theorem. If we have A and B goes to C, and then C represents that's active high, what in order to activate it to active low, what we need to is to add a NOT gate at the end. We can either add a NOT gate or represent that by a bubble. And what I mean by that is new circuit, it's gonna be a NAND gate. That's it. So this circuit right now represents an active low. Now with that being said, let's talk about DeMorgan. The easy way to describe this theorem is if we have a bubble that's going from one side to another across a gate, then if we have an AND gate, it's going to become an OR gate, or the vice versa. If we have an OR gate, it's going to become an AND gate. And here we go. I'm representing these for you. Now, this theorem is convert the gates, but it's keep the same output the same. So let's see how. Let's name the examples, as you can see here, from example 1 to 4. And then take each one and see what's gonna be after we convert it. So the example 1, which we have 2 inputs, 2 NOT inputs, it's gonna be NOR gate. Okay, here we go. So this is example 1. Same way, whenever we're gonna have a bubble on the inside or the outside of the circuit, once it's gonna go over the circuit, then we're gonna change it. If it's or, it's became an and, or if it's and, it's gonna become an or. As we right now seeing in the example 3 and 2. So for this one, it's gonna become an AND gate, okay? And we're gonna go ahead and complete example 4 from an OR gate into AND gate with two NOT inputs. Finally, let's see if our work was correct or there is a proof. Always use the truth table to check what you have done. So the A and B is just a scenario cases of 0, 0, 1, 1. So I'm representing example 1 right now. Here we go, I'm inverting the inputs. So we have A bar and B bar. So C gonna be this 1, 0, 0, 0. Now if we apply DeMorgan theorem correctly, then the NOR gate, which is the conversion, as you can see in example 1, should give us the same output. So here I go on the same cases. So A and B, and the output C should give me the same. And then I'm matching here the outputs, and oops, they are matching. So we have the three signs equal, they are matching. The same way I made here example 2, as you can see, and this is the truth table for both, and it's also matching 1, 1, 1, and then finally 0. Now this circuit, as you all know, this represents the active high circuit, what you submitted for the pre-lab. And our task is converted into the active low as the lab manual instructs us to do. You already complete till the green part in the circuit wiring. So what you need to do right now is to convert all of them into the yellow and the red into active low. Let's see how. Now keep in mind that this yellow is depending on the green and on the red. So we're not gonna add a bubble to the green nor to the red. So we're gonna add a bubble just to the yellow to convert it to active low and then see what's the effectiveness of that change using the DeMorgan theorem. So this is the dashed bubble, and this is the original circuit that I do have. And this is going to the inputs, which they are the green and the yellow. So I'm making the same thing. So this bubble right now, it's going to convert using the Morgan theorem. And this gate, so it's going to convert. So use the Morgan theorem to do this. Now, as you can see, guys, the gate has been converted. The bubble has been transferred to the other sides. What I'm gonna do is I'm gonna shift the bubble all the way to the OR gate of the green and all the way to the AND gate of the red. So I'm gonna have NOR gate for the green and AND gate for the red. In this cleaner version circuit, as you can see, the yellow, let me mark the red also. So the green right now, which is the circuit wiring that you submitted already, is right now active low. Same thing for the yellow, same thing for the AND gate. Now keep in mind that this bubble on the yellow is coming from the bubble that we inserted, while these two bubbles, we did not insert them. These just came by DeMorgan shift. Okay? Keep in mind that the DeMorgan theorem is also work with the equations. So AB bar or not AB is equal to A naught or B naught. That's it for this video. Thanks for watching.